Okay, so I'm going to back up a little bit. I'm excited about starting a new chapter, and this chapter has three parts. It has the scientist part, it has parts of the periodic table, where the transition metals, where the alkali metals, that kind of thing, and that's kind of the simple part. And I'm going to spend most of my time on the part about protons, neutrons, electrons, and isotopes and ions, okay? And so that's what I'm going to be doing. Now, instead of you doing the odd questions for this chapter, what I'm going to do with this packet is you'll just turn in the last part of the packet where it starts to says review, and you can see where one student made part of this and one student made another, but I put them together, and I'm like, it's a nice little homework packet, okay? So that's what you'll turn in a week from Friday when we have our test. All right, so let's take a look at this first page, and I would like you to read the chapter, of course, but when you're reading it, look at this first thing. They have some pictures, and there's something in a bottle, and there's that guy looks kind of old, and he's wearing a wig, and I don't know, where's that from? You know, England likes to do that kind of thing, so maybe somewhere around there. And then you'll see me, I have different kind of writings on there. I wrote them in the book. And so if I were to read that first paragraph, I would notice that humans, have been wondering about what things were made of for a long time. They're talking about the Greeks back then. And, if you're not going to war all the time and you have food and shelter, you can actually form a culture. Cultures don't form very well if you're constantly at war, you're constantly not having enough to eat. You don't need to start doing artwork if you can't even eat every day. And so when you have these societies that seem to be more stable, they develop culture. Sometimes the culture is art, sometimes it's science, sometimes it's math, and that's what we've done throughout history. So, do you think that people thought about what things were made of, even way back when they're talking about, 1000 BC, like that? And so the Greeks, they have all kinds of conversations. They love to have conversations, right? You guys in humanities class, right? You ever talk about the Greeks or Plato, or you ever talk about any? Okay, so they were philosophers. They tried to answer questions. I'd like to ask them and answer them. And they said, one thing they came up with, it was a really teeny tiny periodic table. It wasn't even a periodic table, it was just a table. And how many elements did they think? They thought everything in the universe was made up of only 4 things. What's that? What were they? What were the 4 things that the Greeks thought everything was made of? Say again? Earth, fire, air, or they call it wind, and water. Right. In the 70s, there was a rock group called Earth, Wind, and Fire. Right? Ever heard that one? No? Okay. Earth, Wind, and Fire. That was a big group, and that's only 3 of them, though, wasn't it? What did they leave out? Earth, wind is air. Earth, wind, fire, and maybe they thought it didn't sound good. Earth, wind, and fire, and water. No, that didn't sound very good. So anyway, they were called Earth, Wind, and Fire. But you might think, well, that's kind of dumb. I don't think it's very dumb. They, for example, let's say they thought, here's something here. Hey, how much? You made of earth, wind, water, and fire. How much wind are you? How much air? Not very much. How much fire? Not very much. How about water? Not very much. How about earth? A lot. So some things they just said there's a combination of those 4, and if you were kind of like smoky stuff, you were made more of air than you were earth. So that's what they thought. It kind of made sense to them. But and then throughout the next series, you'll have my advanced chemistry kids actually read an article. If you're just interested in just reading it about alchemy. Have you ever talked about alchemy in a humanities class? So for over almost a 2,000-year period of time, people were dabbling with chemistry. They didn't call it chemistry. As a matter of fact, today we call it alchemy, which they were trying to change one kind of matter into another. That does sound like chemistry to me. But some of them had different goals. Some of them had the goal, my goal is to make money. My goal is to honor God. There are actually quite a few people that They believed that if I could take something cheap, like copper or lead, and I could change it into gold, they thought gold was divine. They thought gold was God-made. And so some of them did it for religious purposes. Some people, they would have a technique that no one else knew. And I don't know if you ever have a mother or grandmother or somebody who makes the best chili or makes the best whatever that anybody's ever tasted. And sometimes you ask them for the recipe, and sometimes they don't want to tell it because it's like they're known for that. Have you ever had that? Have you ever seen anybody who's they don't want to give you the recipe because then everybody could make the best chili in the world? Well, back here, the alchemists would do the same thing. They would even write in weird words, like say the king or the queen, which stood for an element, or the eagle, which might stand for fire. And they would kind of like cryptic language, and you had to be able to decode it. If you know how to decode it in their book of secrets or whatever, then, and of course they would sometimes pass it on to their apprentice, which would pass it on. And alchemy actually, a lot of people think that they were kind of weird people. They weren't. Some of them, they developed glassware. Look right here, it said they developed glassware. They discovered elements. They figured out how to make acids. If you already saw that article that my advanced kids read, they did some archaeology and found that they had made quite a bit of equipment, and it was very scientific in a way. But most of the time in humanity, I bet if you read about alchemy, they're going to say it's kind of like weirdos, and there were some of them that were. Some of them actually did think that there was a mystical, spiritual thing about it. Some of them actually thought there was they were looking for a stone that would transform, a magic stone that would transform one element to another, and they were looking for that. And I agree, there were parts of that alchemy story, but that's almost 2,000 years of history there. Okay, then you go down to, I make quite a jump here, and this picture, this kind of weird-looking guy, he's Robert Boyle. He's very famous, not only in chemistry, but actually in physics. Boyle's law is a real famous physics law. And back then, a lot of scientists were like that, you know. Here's a question I want to answer. Well, then they might go into kind of the chemistry part of it. Well, here's another question I want, and they go into the physics of it. Today, people are very specialized, aren't they? If you knew a scientist, they probably are very specialized in that science, but that's not the way it used to be. Natural philosophers studied all kinds of things like that. Anyway, so Boyle, what he ended up doing, he actually said we need to have a definition about an element, and what's the difference between an element and a compound. So if you had something you thought was an element, how do we know it's an element? Well, we try to break it down, try to break it down. If we can't break it down, I'm going to call you an element. And for a long, long time, water was known as an element. And then eventually they figured out how to break water down, and they said, oh, water can't be an element anymore. Some really famous scientists even thought that fire was an element, and light, they thought light was an element. And eventually they figured out that just didn't work. So it's kind of an evolution of the periodic table also. Okay, so Boyle, another thing that Boyle did, which kind of got out of the semi-science here into what they call modern science. And it says here, Boyle, although Boyle was an excellent scientist, he was not always right. For some reason he ignored his own definition of an element and clung to the alchemist views that metals were not true elements. And so I've seen that before, like Galileo figured out an object in motion has no tendency to slow down, has a tendency to keep moving in a straight line at a constant speed. But even Galileo fell into a trap because he felt like the circle was like so perfect that he even thought that things that were traveling in a circle have a tendency to travel in a circle on their own. And so he even fell in that trap there. So it doesn't mean he didn't have most of the idea down. It's just that sometimes he had a little trap there. Now, one thing, and if you have your book with you, I don't know why the author, almost every chemistry book I've had, except for this one, they have this guy's name here. Now, this is actually even way back in the Greek thing. And so if you have your book with there, go ahead and write that name in the book. Every year I've asked people to do it. It's very possible. It should be written right on that page. All right. let me show you what they're talking about here. All right, so there's a person called Democritus, and so he should be, he's almost every chemistry book I've seen. And he was back then when they were talking about stuff, and they were, I don't know, hey, what do you think the things are made of? What do you think they okay? And so here's a question they had. Hey, what do you think? See this copper? And by the way, this is pure copper, okay? It's an element. What if I take this piece of copper and I cut it in half? Do you think it still has the properties of being copper? And they said, yeah. Well, let's cut it in half again. Yeah. They keep doing it. And for whatever reason, they weren't really scientists, they were philosophers, and they said to themselves, what if I kept cutting that in half? Could I do that? Is it infinite? Is matter infinite? Meaning, I don't care how much, keep cutting it, it's still copper. And there were a group of people that said, matter is infinite. You can just keep cutting, it's still the same material. And then, for whatever reason, not scientific, Democritus says, I don't know exactly why, but I think there'd be a stopping point. I think you get small enough, there's going to be something down there that if you cut that in half, it won't be copper anymore. That means matter is finite. Does that make sense to you? It's finite. Now, I don't even know the names of the philosophers who thought the other way. You know why I don't know it? Because later we discovered that this was correct, that Democritus was correct. That's why his name's in the book, and whoever the other people were, they're not in the book. And so we actually do think that matter is made of pieces that if you cut them in half, it won't be that material anymore. Now he used the word atomos, and atomos meant indivisible. He thought it would get to the point where you even couldn't divide it. You couldn't divide it, and there's a stopping point. So it's indivisible, not dividable, and he called that atomos, and now that's why his name should be in the book, because we use the word atom, don't we? You get that? Okay. Is everybody okay with that? All right, so that's a little quick history, and I'll do some other scientists later, but that's enough for today's scientists. So I'm gonna move on to the other thing we're doing. All right, let's go over here now. Excuse me. Okay. I know. Let's do, since there are 3 different sections, all right, let's do another one. Everybody see the periodic table? Okay, everybody see that? All right. See this little guy here, this little stair step? That guy there? Okay. Okay, now bring hydrogen way over here. Bring him over here. And hydrogen and everybody on this side of the stair step, those things are called nonmetals. Okay? And you'll need to know that for the rest of the year. Those are nonmetals. And guess what? Almost 80% of the elements are. They're metals. If you have a chance to come over here, there's a periodic table on the wall. And it's called a pictorial periodic table. And it actually shows you every element, what they look like. Pretty boring, isn't it? Look, gray, black, gray. Oh, what's that? Gold, copper. There aren't too many things over there that are very exciting. And so that's pretty neat. God had a building block set, which was boring. Look at that. Look what it looks like. Man, that's boring. And yes, look what he made out of it. Look what you can make. If you combine the elements, what can you make? Red, orange. See that? All these things that we know of are combinations of, if you're not an element, you're a compound or you're a mixture. Is that right? So anyway, I do need you to know these are the nonmetals, including hydrogen. And then most of the things are metals. And nonmetals they want to try to pull electrons away from you. They like to gain them. And these guys like to lose electrons. So that's where I'm going to start my lesson here. And one more, and I'll start with the periodic table. Everybody know what these are called? Noble gases. When I was your age, they were called the inert gases. The inert gases means they don't like to react at all. These guys like to react because they like to gain electrons. These guys like to react because they want to lose electrons. These guys don't want to react because their electrons are in a stable configuration. I'm not going to gain them. I'm not going to lose them. We're not going to do much chemistry with them, are we? The next chapter, we learn how to write compounds. I'll say, what's a compound that forms between sodium and oxygen? Okay, we'll learn how to write formulas. But guess which ones we know what we're talking about? Those. So, all right. So now what I'm going to do is go to the chart, and we're going to spend most of our time, like I said, in class on that. I'll try every day do a few scientists, and if every day try to do a little bit on the periodic table, and then we'll get to the main thing here. All right. I'll bet you remember a lot about protons, neutrons, electrons. Is that correct? Or not? Did you have that? There's no way you would not have had this in 7th or 8th grade. But let's pretend that you never have had this. How about that? Can we do that? I'll just pretend you haven't. And I'm not trying to bore you, but just hang on, stay with me, okay? All right, here we go. We know that some of the scientists did experiments, and they did not know what an atom was. At one time, they didn't know there were atoms. And then they said, I think maybe there are. And they did experiments and say, I think, everything's made of these little tiny atoms, all right? And then they didn't know anything about an atom. And they had different models of an atom. Oh, atom must be like a ball. I bet it's like a ball-like thing. I don't know why they thought it was a ball, but it's like that. And then somebody did an experiment where it seemed like you could take part of an atom off. It's like, if I do this to atoms, something comes off of the atom. And we'll talk about that tomorrow. And they eventually figured out there was a negative part of an atom. That's strange, because atoms, they're not charged. Look, I didn't get shocked. They're not charged. And yet, we can do something to that and make some negative stuff come off. Well, how can you have negative stuff come off an atom if you're neutral? Well, maybe you must have some positive things too. You see that? So they eventually figured out there were things smaller than the atom. And that word that we use is subatomic. Okay, sub means below or under. See that? So the subatomic particles that we talk about in chemistry class, now if you were to take some higher level physics classes, they would talk about subprotonic. That would be some of their subatomic particles. They get into things like quarks. Raise your hand if you ever heard this. Quarks, neutrinos. Okay, we're not going to talk about those in this class, but the subatomic particles we're going to talk about are protons, neutrons, and electrons. Everybody okay? Now, I'm going to teach this a little bit differently than they would have done in middle school, okay? Yes, you have to memorize certain things, but notice that I had this thing drawn here. And this is called a brick wall, okay? So if it doesn't look like a brick wall, it is. Now, what I need you to do is, as I'm teaching this, there are two parts of the atom that I want you to know about. There's a world of mass, and when we're talking about the world of mass, we should not be thinking about the other world. And then I'm going to have you crawl over that brick wall in your mind. You're going to build a brick wall in your mind and say, here's my compartment for the world of mass. Here's my compartment for the world of charge. Now, if you can keep those two worlds separated, you'll absolutely understand what's the difference between an isotope and an ion. If you try to do this, if you try to mix those two ideas, you're going to get confused. You get that? So I'm going to show you how this works. In the world of mass, by the way, do you know how much mass is a proton? What is a mass of a proton? How much is it? Take a guess. What is the mass of a proton?
The answer I found is 1.008 atomic mass units.
What is the mass of a proton in grams? What is the mass of a proton in grams?
The answer I found is 1.008 atomic mass units.
You. Try one more time. How many grams is one proton?
What would you like to convert into grams?
Wow. I do this every year, and I've never had them do this to me. What is the mass of a proton in grams?
The answer is 1.6726 to 1911 times 10 to the negative 24 grams.
Okay, sorry, I had so much trouble there. Now, I don't memorize that number because I'm not going to use it. If I were a nuclear physicist, I might want to use that number, and I might memorize it. But what's the mass of a proton? 1.67 times 10 to the what? Negative 24? You mean decimal point, 23 zeros, 167? Yeah. That's not very much. That's right. Now, we could go around and say, and I could teach this to you and say, remember the number. The scientists are real people. And here's what they did. They said they found out that the mass of a proton and the mass of a neutron were almost identical. Again, if you become a nuclear physicist, you can talk about why they're not exactly the same, but they are almost the same. You get that? Now, I could put that number right here in grams and put this number here in grams. But because a human before me said, I hereby declare that this much mass, I'm going to call it 1. 1? 1 what? Not 1 gram. You better not ever call a proton have a mass of 1 gram. A paperclip has a mass of 1 gram. There's no way a proton has a mass of a paperclip. 1 what? And maybe for a half a second they said, I'm going to call it 1 teeny tiny mass unit. And the other scientist said, slapped him and said, let's be a little bit more adult-like. Okay. We're not going to call it a teeny tiny mass unit. Atomic mass unit, also known as AMU. All right. What's the mass of a proton? 1.67 times 10 to minus 24 grams. Ugh. I'll forget that tomorrow. I'll forget that after I leave class. How about this? What's the mass of a proton? 1. 1 what? 1 AMU. What's the mass of a neutron? Oh. Okay. What do you think about that? Now, I have looked this up in several books. I cannot get the same number, but I'll use the last number I saw. Okay. 1 over 1,866 AMUs. How much is that? All right, here we go. 1 divided by 1,866. 0.00053 AMUs. Now, again, you're looking at me and saying, oh, I got to memorize that number too, because I would have get an A in this class. No, let's not do that. All right, look. The biggest element I know up there is 118. Element number 118 has 118 electrons. You know that? I would need to have 10 electrons to make this number, 100 electrons to make that number, 1,000. If I had 1,000 electrons, I might consider the mass of an electron. If I had 1,000 electrons, it'd only be 0.5 AMUs. You get that? So, for this class, what are we going to say? The mass of the electron is 0. If I get it? It will not come into play. The mass of electrons will not come into play. So, here we go. Look over here. In the world of mass, atoms are made of protons, neutrons, and electrons. All right. 2 of these have a mass of 1 AMU apiece. The other one is a mass essentially 0. Where are they located? Where are protons located? And that's part of the story here, but you know this. I know you know this. Raise your hand if you know it. Raise your hand if you know it, but you don't want to say it out loud. Oh, there's no way. What is it? Where's it at? Oh, you didn't want to say. Where is it? It is. Okay, so the nucleus would be the center of the atom, wouldn't it? Is that correct? Have you had this? again, I'm going to teach it like you haven't had it, but at least give me a little help and say, oh, I had all of this, okay? Then I'll know I can go a little faster, but not, I'll just go at that pace. Where do you find the neutrons? Matter of fact, we have a name for that. If you're found in the nucleus, oops, I just spelled it wrong. You're a nucleon. What? What's a nucleon? What's a nucleon? Particles, help me, John. A nucleon are particles that are found where? In the nucleus. And what are the two nucleons you know about? Everybody got that? Where are electrons found? Not in the nucleus. Now that's for another chapter, but electrons, I'm sorry to tell you this, in elementary school, I would probably teach that electrons went around the nucleus like little moons around a planet. I might do that. Even in the 9th grade, you did this thing, it's called the Bohr model, didn't you? The Bohr model, you had the nucleus, didn't you? Didn't you draw little circles and put 2 electrons in the first energy level? Didn't you put 8 in the next? Miss Fallon still does the Bohr model, right? All right, that's okay. You can use that model to at least learn something about the atom, right? But as we teach later, we'll do this thing called quantum mechanics model. You'll find that there is zero evidence, that they're going in circles. You're not even going to like the real answer. The real answer is we don't know what they're doing. We may never know what they're doing. They're doing something, and I can tell you where they are 90% of the time. I can give you this zone that they're in, this electron cloud, this area. But I don't know what they're doing. How'd you get from there to there? I don't know. Did you go in a circle? We have no evidence you're going in circles. You go like this? I don't know. Now that's not for this chapter. This chapter, we'll hold that later. Well, that's a little. But for right now, if you look at this, you know that 2 of these are in the nucleus, and all the mass, essentially then, think about that. Then essentially, 99.99% of all the mass is found in the nucleus. So if you want to know how much the mass of an atom, you need to look in the nucleus. Have I got that? So I have a model here. It's a Bohr model. Again, I did draw circles just so they wouldn't move around. If they move at the speed of light, you'll never see them. Is that right? So I thought I'd just let them sit there and be like a static model. Okay? Stay right there. Stay right there. Now, it's also incredibly out of scale. Incredibly out of scale. Show you in your book. All right. Can you see us drawing in here? Okay, here's a typical atom, and the counting all the electrons. Here's an atom whose size is about 10 to the minus 8. Did I say 8? Yeah, 10 to the minus 8 centimeters. That's pretty small, isn't it? That's really small. But watch this now. How big is the nucleus compared to the diameter of the atom? 10 to the minus 13. What does that mean? What does that mean? The nucleus is how many times smaller than the atom itself? 10 to the 8, 10 to the minus 8, 10 to the minus 13th. How many powers 10? Separate those. Here, I need some more input. Come on. How many powers 10 separate the size of the atom from the size of the nucleus? How many? Ethan, you know. You know you can't subtract 13 from 8?
5.
Okay, thank you. Now, is it 5 or 10 to the 5th? How much smaller is the nucleus than the whole atom? Ready? You can divide it, you get 10 to the 5th. What is 10 to the 6th is a million, isn't it? What's 10 to the 5th? Come on, I need some more input. Say it again. 10 to the 6th, a million, so what's 10 to the 5th? 100,000. the nucleus of most atoms are 100,000 times smaller than the atom itself. So if I were going to make a real model of an atom, I'd go probably to a baseball stadium, and I'd put something about this size, maybe a pea, a little green pea. I'd put it at second base, and that'd be the nucleus, and then my electrons would be past the home run fence. That would be a good model of an atom. But guess what? That won't fit on a book, will it? So most of the time when you see drawings of an atom in a book, they're going to be out of scale, aren't they? They're way out of scale. But I have to get it on the paper, don't I? So terrible model for scale size, but I had to make it big enough so you could see it. Are you with me this? Okay. Oh. I thought I fixed that. Okay, sorry. Terrible model for size, but I had to make it big enough so you could see it. Okay. All right, we're ready to look at this Bohr model, and here we go. This is the foundation of a lot of this chapter, okay? In the world of mass, I have protons and neutrons. Let's go down here and visit the world of mass is also known as the world of the what? The world of the mass is equal to the world of the nucleus, isn't it? Let's go visit the nucleus. Hey, how much do you weigh? 1, 1, 1, 1, 1, 1, 1. What is the mass of this atom? We're not looking at the electrons. What is the mass? 7. This atom has a mass of 7 because there are 7 things in the nucleus, and each one of them has a mass of 1, doesn't it? Now, you probably remember this from middle school. How many protons do we have? 3. Look on the periodic table. I promise you, any atom that has 3 protons, you must use this symbol. If you have 3 protons, you must be lithium. Period. Now, whoops, I put it in the wrong place. Sorry. You must be lithium, and and I'm going to tell you that the atomic number will always be the number of protons. Now, you know why lithium's number 3 on the periodic table? It wasn't like one day they shook up all the elements and threw them out of the hat. Lithium, you're number 3. No, it wasn't that. If I go anywhere in the universe and I find an atom with 3 protons, it's lithium. And so the atomic number is like a fingerprint. You are number 3. You have to be what? You have to be lithium. Now, let's go down here, and I'll show you how to draw the symbol. Capital L, you know, you only have one capital letter or one capital, one small letter. We learned that a long time ago. Now, chemists were pretty smart here. I like what they did here. By the way, if you get an older book, they didn't, but eventually they fixed it. See the 4 corners? Okay, every one of those corners is kind of reserved for some information. Now, I remember my son, he's like 42 years old now, but my son, when he was younger, I always liked baseball. But one of the things I would do with him, this has nothing to do with chemistry, but every time I tell the story about the 4 corners, I usually have to tell the story. So when you're telling a little kid how to catch baseball, you know, first of all, they catch it, and the idea is to make sure they catch it, doesn't hit them in the face. So if you can, you try to get them to catch it over here. See that? And they're pretty good at catching over here. And you do that over and over and over. See that? And then the harder one is to make them catch it across their face. See that? That's harder in baseball. Any baseball players in here? Okay. Well, anyway, so they did this pretty well. Okay. Now the other corner, see? That's harder. Okay, what's another corner? I'm going to... See that? And real hard one, oh, that's hard. So we would practice that, and I would throw it at all 4 corners, and eventually, any of you play, nobody here plays baseball? Wow. You don't play baseball? Okay. So you don't know what I mean, but for you, it's pretty easy, isn't it? Catching all 4. You ever play with anybody else who didn't play baseball and they had trouble? They have trouble. All right, let's go back to chemistry now. Chemistry has four corners, and this corner here in the upper left-hand corner, this is always reserved for the world of mass. So now I look up here, what's the mass of this atom? It's 7. So this is lithium-7. Now, they have a name for that. The mass, the element has a certain mass. This is called lithium-7 isotope. Oh, here we go again. All right, on this side of the brick wall is the world of mass. Electrons don't matter. Electrons don't count. The world of mass includes the world of the nucleus. And the world of the nucleus is the world of isotopes. This is called the lithium-7 isotope. Every atom in the universe is an isotope. All of them. Now, lithium-7 is this isotope. Now, I want you to look up here now. What would happen if I were to take away one of these neutrons? By the way, this is a proton because it has a plus sign, and this is a neutron. Now, look up here. What if I were to take away one of the neutrons? Would it still be lithium? This is the absolute essential. Today's lesson is essential. If I took away a neutron, would it still be lithium? And I told you that the number of protons will always tell you what you are. Do I still have 3 protons? Then I would still be lithium. But this one would be called lithium-6 isotope. Let's take away 2 neutrons. Is it still lithium? Yes. It would be called lithium-5 isotope. Oh, okay. All right, let's go back here. Everybody got that? Now, what I'm going to do is flip this over, and we'll come back to the world of charge in a minute. I have drawn for you 3 different elements. I'm sorry, 3 different atoms, sorry. I have drawn 3 different atoms, and what I want you to do is I want you to see if you can fill out that box. Fill out that box, all 9 boxes, and I'll give you about a minute. So let's take about a minute to fill out all 9 boxes. 3 different atoms. What's the atomic number? The number on number 1. What's the atomic number? What's the mass number? What's the mass number? What's the symbol? I like that. Looking back, checking back on that other page. All right, Jonathan, you're going to help me there, right? Jonathan, what is the atomic number of this atom? How much? How do you know that? Okay, what about this guy? How much? How do you know that? Okay, how about this one? Okay, all right, good job. If you had 111 across there, you understood that the atomic number is the number of protons. All right, let's go with Noah. Ready? Ready? You do the next one. What's the mass number for this guy? How do you know that? What about the electron? We don't count their mass, do we? No, we don't. How about this guy? How about this one? How much? 3. Yep, there you go. Very good. All right, how about Danielle? What symbol would you give for this atom?
That'd be H.
What is it?
H.
Capital H, right? What about this one?
Would be 1H.
What now? You mean like this? Or is that what you mean, 1H or just H? Okay, what about this one? 2H, what does that mean? What is it? You mean an H with a 2 on it? Is that what you mean, like that? Is that what you mean by 2H? What do you think? Kayla, what do you think? Do you like what she said there? Would you put a capital H there? You would? How about this one? Would you put capital H here? Real loud, I can't hear you. H-E? Okay, so you put H-E, right? What do you think about that? What makes you say H-E for that one? What now? The mass number is 2, right? Okay. But what is the atomic number? And what does it say the atomic number is? Number of protons, right? And one thing, since we're just learning this lesson, you need to know that the atomic number is the fingerprint. The atomic number will identify the element. And if you have an atomic number of 1, you must be hydrogen. See this guy here? You must be hydrogen. See this guy here? You must be hydrogen. Now, this would be confusing for anybody. 3 different atoms have the same symbol. Which one did you mean? So what we do is we have to use the world of mass to distinguish those, all right? So let's go with Max. How can I make these look different to tell you which atom I really do mean? How can I do that?
Wait, the charge?
What'd you say?
The charge of it?
Wait, what side of the brick wall are you on? I'm on this side of the brick wall. We're not going over there, are we? We're not going to charge, are we? Not till we figure out the world of mass. I'm still in the world of mass, so don't say charge. Don't say electrons. Okay, what do you think? I'll give you a clue. If I put a 1 there, it means this atom has a total mass of 1. Is that case? Is that the case or not? Does he have a mass of 1? He does. All right, Max, do the next one. What do we do with this one?
2.
Yes. See? See? And what about this one?
3.
Yes. Everybody see that? Now, atoms of the same element that have different masses because of different number of neutrons, what do we call that? Atoms of the same element, but they have different masses. What do we call those? Isotopes. Got that? Now, when I was young, a long, long time ago, I know I was taught wrong. I didn't know it was wrong, but I remember a teacher saying, well, this is hydrogen, and these are the isotopes of hydrogen. And that was okay because they were the teacher. I didn't question that. But let's imagine you know somebody who has 3 sisters in the family. Betty, Lou, and Bobby. Okay, Betty, Lou, and Bobby. And I say, which one is the sister? Which one's the sister? So you can see what I was taught was wrong because they said this was hydrogen and these were isotopes of hydrogen. That's wrong. Betty is the sister and the other, no, Betty's the girl, and it didn't even make sense, does it? The only way it makes sense is to say all 3 of these are isotopes of hydrogen. Yes, no? All 3 of these are isotopes of hydrogen. Now, it just so happens that over 99.99% of all the hydrogen atoms that we've ever known in the universe are like that. But these are still all hydrogen. Can you make water out of these kind of isotopes? Yes. Most of the time when you see water, it's made of, it's H2O, but each of the hydrogen atoms is going to have a mass of 1. So if you pick up a bucket of water, you know kind of what it feels like, don't you? Now, if I wanted to spend a little more money, I could take and make water out of the isotope that had a mass of 2. Now that would not feel the same. That would be a type of heavy water. It would be type of heavy water because every one of the hydrogen atoms of the billions and billions in there actually weigh twice as much as they do here. So this would be water. Sorry, that's probably a flood alert. Okay, sorry. I'm gonna stay right here. So, all right. And then you could make water out of this isotope of hydrogen, and it would not only be heavy water, but of the 3 isotopes of hydrogen, only one of them is radioactive. So isotopes can have different masses, and some isotopes could even be radioactive. It just so happens that hydrogen only has 3, only one of them is radioactive. Now, also, when they first learned about isotopes, maybe they thought, well, we got to start naming them because, humans like to name things. And they said, okay, let's give a name for this guy. Prototype. What's a prototype? What does it mean, a prototype? It's the first one you make, isn't it? Protium. Yeah, you're hydrogen 1. And even though when 2 people sing, it's called a duet, that's close enough for me to a memory trick. What is deuterium? What's the mass of deuterium? 2 people singing a duet, I can remember that. And I don't know about you, but my tricycle had 3 wheels, and tri means 3, isn't it? Tritium. Now, even though it was kind of cute, and it's very human to want to name these, I can tell you right now, I don't have these memorized, but there are some of these elements up there that have 8 different isotopes. 7, 5. I think they're humans. They said, we got to stop doing that. We got to stop naming those isotopes. And so here they did. Except for the hydrogen isotopes, except for them. Those are the only ones I know of that have special names. Here is the name of an isotope. This one is called carbon-12. Here's one. Carbon-14. Here's one. This is what they use for bombs. Uranium-235. See? Kind of boring name, right? Not cute. No cute names. Just, it's the mass, isn't it? So this could be called hydrogen 1. This could be called hydrogen 2. This could be called hydrogen 3. If I ask you to point, say, on the periodic table, ready? Point to tritium. Go. Point to tritium. It's up there. It's hydrogen, isn't it? It's hydrogen isotope that has a mass of 3. What do you think? Okay, so we need to stop. And if you feel like, right now I can see you looking up some scientists or any of the homework, if you want to try it, you can do that. But I think after a couple more days, you'll be able to do most of this stuff. And also, hey, help me